Hello everybody, today we have a pretty interesting problem called flatten a multi-level doubly linked list. So we're given a doubly linked list like this, and we're supposed to flatten it into one flat list like so. So how do we do this is that we probably have to do so basically what that means is that we have to move this 11 and 12 behind the 8, as you can see here. Let me zoom in if I can. I can't zoom in. Okay, well, let's make this bigger. So you see this 11 and 12 that goes before the 8, and then you have to take the 7 and go after the 3, but you have to put this whole entire list before the 4, which is here. So basically you just have to recursively flatten this list. So you go all the way to the bottom of this linked list, you grab that linked list which no longer has a child, right? So you go all the way to the bottom, it goes all the way back, right? There's nothing to flatten any longer. Then you take that node right here, and you point it, you lose the child node, you point it as the next node, and the next previous node points back at it as this tail as the head, and then we got it squeezed right in between the two nodes, and we have done the flattening. And so let me show you what I mean. So let's just say we have a very simple case, the base case. We have 11, 12. We have no childs, right? No children. So basically that means that we can return it. We straight up return base case, right? Then at the next level, since we do have a child, right, what we're gonna do here is that we're going to move this item next. So we have 7, we have 8, we have 9, we have 10, right? So this is gonna be next, this is gonna be current, this is gonna be next pointer, right? Or this is going, yeah, current next, doesn't matter, previous current, current next. So we're going to squeeze this base case with this head pointer and this tail pointer, and we'll take the head pointer, point it here, point the head pointer back at the current pointer, take the tail pointer, point it next to next pointer, and the next pointer point it back to the tail pointer, and that way we basically get rid of all the pointers from all of these things, and we're good to go. We should have this 11, 12 squared away inside this point here. And with that, we can go through this, we'll go through all the way to the end again, right? Once we get the tail, we have basically eliminated all the child nodes, and we're good to go. We take this and we hit the base case. We hit the base case, we're good. And once we get the head and tail, then we shift it back up. So the plan is head and tail get, then return as base case. Okay, base case maybe none. So basically we still need to think about the edge cases at this point, but that's my first thought when I read this problem. That's like immediately I thought recursion. Let's think about match. So match is recursion, and think about the base case, getting to what we need to do, and that's the immediate thought. Okay. Of course, I did not think about the understanding part yet at all, so I just basically skipped that. But we're coming back to that because I want to get through my first thought immediately, because I think that's that's an important thought. It would come out first, and you should think about it. So this is another base case. So this is a very simple case where we can see how it works, right? Here we have the head and tail node as 3. So that's another edge case because we did not cover that in our edge case earlier. So we have this 1, 2, and then a 3 pointer, and we need to shift this in. This is the head and tail node, and this is the current and next pointer. Now, what happens if there is no next pointer, right? what happens if there's a single node? Okay, sometimes there are no nodes. But what happens if that's another edge case? We have a few edge cases here. And what happens if we have 1, 2, 3, 4, and there is no next node? Well, I mean, that's a problem. Like, how do we handle that? There is no next node. We still have to point it at the current. That's fine, but we have to handle the case where there's no next node. So we have to handle a vertical linked list where there is no next node. That's something that we have to consider in our plan. So let's put that in there. Right. So base case, set current dot next to head, and next dot previous to tail. As maybe if, and if next, then next previous to tail. Okay, so that way we don't end up with a we handle that case because we have to handle that. So that's the edge case. And what if there's none? We just return none then. There's nothing to return. And just return none for this edge case. Just return none. If none. Okay. Great. So that's something we need to get through first. So first thing we need to do is recursively get the head and tail node. Once we have the head and tail node, like how do we know we got tail node? Well, we know we got tail node because next is none. Like the current dot next is none. Basically, there's nothing there. That's the tail. And the head, well, that's the starting point. We know we get it. So we know head because we recursively get it. So in this case, flatten, we do get the head, and I think we can just do this whole entire thing in terms of just flat out like recursion, like immediately. I think with that, our plan is pretty set and clear. Let's go do this problem and see what sort of things that we don't know and how we can, like, what we can learn here. So implementation. Because, I mean, the only way we can get good at implementing these solutions is to implement more and more plans out there and figure out what we don't know, what we're struggling in in implementing, and we can get better at it if we just do more problems. So first things first, let's do the base case. So current equals head, next equals head.next. Something is wrong, and that thing is if not head, return next. Return. Just return none, please. That's the first thing we've taken care of. Let's put a check mark behind that, or exclamation mark, something somewhere, just to make sure we have handled that. So let's put a hash mark, like we handled that. Okay, so current equals head, next equals head.next. So what happens if we don't have like next? That means so while next, basically while there's a next, let's continue. Okay, so what happens is that once next is gone, tail is equal to next. And what we're going to return to the next layer is a head and tail so that they can handle it. In this flatten solution here, what we have here is we don't have a function that returns just a head. We return both the head and tail. So that means immediately that we need a separate function. Let's just call it DFS. And this takes a head and gets us back head and tail. And yeah, so basically this grabs a optional node. Looks like there's some like this quotation around it. Let's do that. So this is great. Now we have an optional node. We have a tuple of this optional node thing. We know for sure that that's what we're gonna do. Okay, so, and we know for sure that there will be a head because this is a child node. Child, if it's okay, so while current so we set it to head and head.next, and we want to handle only the current item, and so let's just set this much because we only need this much information because we don't want excess information. That just makes it more difficult for the next reader. So current.next is next. So currently what we're doing here is just iterating through the top layer, right? And if we have a child, if the cur has a child, cur dot child, if there's a child, then that means we need to get the head and tail. So we can say get head and tail. So get head and tail of this particular child, cur.child. And we're gonna fuse it into our item. So we're gonna grab the head and tail, and we basically take that and we just grab the we set that as our head and tail. So cur.next is equal to head. Head.prev is equal to cur, and tail.prev is equal to next. No, stop myself. So next.prev is equal to tail, and tail.next is equal to prev. With that, we have reset everything. And last things last, we just need to set our cur equals next, and we go until we are pointing to none. So one thing to note is that we need to handle this case where cur if that there is no next. If next, then we do this. If not next, then we don't have to do anything, right? Perfect. So with that, we have covered all this logic, right? So here's the question. In the get head and tail function, are we going to call flatten? Because on each node, because when we get head and tail, it's like we flatten one layer. But because we only flattened one layer, there could still be other child nodes, right? And when we run get head and tail, what we want is the head and tail. But of course, we need to continually flatten our items inside. So I think what we need to do is also run these flatten type, this code basically, inside our code, because flatten only returns a head, but we need both head and tail for our solution. So let's just grab this and paste it in. Do you know, I mean, actually, like, we don't really need to make two functions. We can just grab flatten and just iterate the whole entire, like, the head all the way to the end, and then grab the tail, and then, you know, set it up that way. But I think that will take much more time complexity, because we have to, like, go through it multiple times, and with this we only go through it once for each run. By multiple times, I mean we have to, like, grab this head, right? We figure out all the tails, we get to the end, and then we basically send this head back up, and we have to find the tail of this, like, thing. It'll be easier to implement, of course. Definitely easier, but it's not the best. Okay, so here we go. Current equals head, because we know head must exist. It must be a node, because but that's not necessarily the case, because yeah, I'm not sure. I'm pretty sure that must not be the case, because whenever we're running get head or tail is that if cur.child exists. And yeah, that's basically what it means. So we're getting the head and tail, we're moving the cur, we keep getting the head and tail until the point we can return the head and tail, right? What is a tail? Well, the tail is basically, yeah, it's gonna be prev, right? So we need previous to be one step before cur. So because we know that when we do next, if there's no next, if not next, tail equals next. Okay, we got that. That's cool. If there's no next, create the tail and finish this loop. We're ready to return the head and tail. And basically we have flattened our list. Perfect. With that, this top portion, we don't need the tail, we don't need that code, and we just return the, we can return the head. Perfect. With that, I hope this works. I'm not sure if it will or not. I'm pretty sure I addressed all of the issues here. We addressed recursively getting the head and tail node. We know that the tail node exists. We got the tail node because current.next is none. we know the head because we recursively get it. Yes. Head and tail gets and return as base case, none. Okay, we did that. We set the current dot next to head, and then if next previous, we did all that. We have to handle a vertical linked list if there's no node. Yes, we handled that because there's no tail node. We have no problem. We handled that. And yes, let's return and see what happens. I'm not sure what will happen. And we might get some errors. We might get some issues. But this is part of implementation. And this is just part of code. Like, we're never going to write perfect code the first time around. Let's check it out. So get head and tail has not been initialized yet. Let's put that at top then. We could also just do better by doing this instead. So just put a self in here. And that way we can call it from anywhere. That's might be better. Hopefully it works. Not sure if it will. No one knows until we run the code. Okay, we have an error. Let's check it out. Prev. Oh. What? Prev. What are you talking about? Cur, please. Tail.next is equal to next, please. What am I thinking? I don't know how that came about. Let's run the code. Okay. Next is none. Attribute. None type has no attribute next. If tail is none, basically we basically returned none for tail. If not next, tail equals next. No, tail's equal to cur, please. My bad. Not a validly doubly linked list, so we have an issue. It's time to debug and see what's happening. Looks like what we did is that we returned 11, 12, 9, 10, and so on and so forth. And we're missing the head. We're missing that portion. That means we have changed the head. Oh. Which, well, this is, we're gonna have to say our master head. Let's return the master equals head, because we use the head as a verbiage here, and we're returning the master head. And we also need a master head here, because we are using the verbiage head later too, and we're just changing it the whole time. So let's run the code. This way we don't mess everything up. Okay, we have 1, 2, 3, 7, 8, 11, 12, 9, 10, 4, 5, and 6. But it is not a valid doubly linked list. Okay, so what's the issue here? Why is it not valid? I'm gonna have to go look this up because I'm not sure what this error implies, and I think that'll take some time. So I will pause the video and I'll come back. Okay, so I debugged the code a little bit, and I found out that the child node was supposed to be set to none. We can no longer have any child nodes. And so we have to set all child nodes to none after we're done with the operation. It looks like the example cases worked out, and we have solved all the problems that we have, but we don't know if this works if we submit it. So this is, we're going to submit it, and we have the wrong answer. And so what we have here is a 1, 2, 3, 7, 8, 4, 5, 6. For some reason, we have 4, 5, 6 from somewhere. And what we're missing is 11 and 12, and then 4, 5, 6. Must have to do with some sort of like recursion error that we've gotten. Okay, hello there. We're back, and I found the error that we had. The problem was that though we recursively gone through our items, we were not getting, what we were not getting is the next item. By the next item, I mean like we were attaching it to the head, but we were not returning the correct tail, and with that we attached things incorrectly. So with this, instead, we iterate through all the heads again, and that way we can basically get our solution. But that just means that we had to redo everything once more. It's not very different from what we had done earlier, but we have solved the problem. It's not the best solution in the world. We were able to debug it, and here we are. So I do say that I will come back with a second video to make a better version of Flatten for you. And it will just be the implementation. It will just be an amendment to this video if you want to check that out. Now, it'll be linked in the link in the description below. The evaluation is, again, O of n, because we go through every single node. And yeah, and the space complexity is going to be the memory used for each child node, so the height of the tree. So with that, if you have any questions, please comment below. If you enjoyed this video, like and subscribe. Want more videos like this, like and subscribe, and I'll see you in the next one. Alright, bye.